In this and the next few lectures in our series on path integral quantization, we are going to talk about coherent state path integral quantization. Within the framework of non-relativistic quantum mechanics of the kind that we have been talking about so far, this gives us yet another approach towards the calculation of the path integral. However, it's actually a lot more than just another way of calculating a path integral, and especially when we go over to relativistic theories or field theories, it helps us to open up new avenues. The standard path integration techniques that we have been talking about so far earlier in the series actually are all based on what is called standard canonical quantization. Coherent state path integral quantization allows us to go beyond that. In particular, this is especially useful for systems for which there are no classical counterparts. Canonical quantization essentially starts with a system which has a well-defined classical counterpart, takes a look at the standard classical dynamical variables like position and momentum which are available in this system, and then elevates them to the role of operators. However, if a theory does not have a classical counterpart, this approach cannot be directly used. For example, in a theory of fermions, the antisymmetric behavior does not have a classical counterpart, and we would be at a loss if we were to try to do standard canonical quantization with fermions. These are the cases where path integral quantization using coherent states becomes very important. Now, in today's lecture, we will not talk about path integrals at all after this. What we will do in this lecture is introduce the notion of what coherent states are. Coherent states are, of course, very, very important entities in quantum mechanics, but unfortunately, they are not often taught at the level of detail that they deserve in all courses. So, to ensure that everybody has a level playing field, I will devote today's lecture essentially to properties of coherent states, and we will talk about a very simple kind of coherent states, the harmonic oscillator coherent states. The arena where the coherent states live is one which is pretty familiar to all of us. It is the Hilbert space which is spanned by eigenstates of the harmonic oscillator Hamiltonian, the number states, ket n, where n ranges from 0, 1, 2 and so on for all non-negative integers. And the major players in this game are, of course, the standard raising and lowering operators, which are familiar objects from the theory of harmonic oscillators, A dagger and A, and this, of course, is a very familiar commutation relation which A and A dagger obeys. And is, I'm assuming, also well known to all of you that A and A dagger act on the number eigenstates n in the following manner. A lowers the energy eigenvalue, or in this case the number's eigenvalue, and A dagger raises the number eigenvalue by 1. And this nth number eigenstate can be obtained by starting from the eigenstate corresponding to n equal to 0, applying A dagger on it n times, and dividing by an overall factor of square root of n factorial to get the normalization right. And of course, these n's are nothing but the eigenstates of the number operator n hat, which is A dagger times A, and that is A dagger A acting on n, this ket, gives you this ket n times the number n, which in this case is a non-negative integer. Now, the n's are eigenstates of the number operator. The other important operators in this game, of course, are A and A dagger, and a natural question to ask would be, what are the eigenstates, if any, of these ladder operators A and A dagger? Now, because A and A dagger are non-Hermitian, you may find this question a bit surprising at first if you have not seen this already, simply because eigenstates of non-Hermitian operators are not that useful, usually, in quantum mechanics. But it turns out that the eigenstates of the operator A are actually very, very important, and these are nothing but what we call the harmonic oscillator coherent states. The fact that the operator A, the lowering operator, has at least one eigenstate is rather obvious. Remember, our ground state, ket 0, is actually killed by the annihilation operator or the lowering operator. A acting on ket 0 gives you 0. This of course means that the ket 0 is actually an eigenstate of the A operator corresponding to eigenvalue 0. But are there any other eigenkets of A? The answer is yes. And to see that, what we need to do is start by assuming that the eigenket of A is given by ket alpha. A operator acting on ket alpha gives you alpha times ket alpha. At this stage, I am not making any comment about the nature of this number alpha. It's the complex number at this stage. And since our Hilbert space is spanned by the number eigenstates n, every ket in the Hilbert space, including our alpha, can be expanded in terms of the number eigenkets with appropriate coefficients. In this case, I am assuming that ket alpha is given by the sum over all n from 0 to infinity of Cn times ket n. Now, if I apply the operator A on alpha, what happens is simple. The operator A acts on this particular linear combination, and being a linear operator, it jumps across the Cn and hits the ket n. And we know what A does to ket n. It makes the ket become a different ket, the eigenket of n hat corresponding to eigenvalue n minus 1, with this as an overall factor in front. Now, in order to make this look a bit more like the Cn that we started out with, what we will do is change the n label here to n plus 1 so that this n minus 1 becomes n. Of course, that means all the n's everywhere increase to n plus 1, whereas the starting value of n here has to start from minus 1. Just to check that we have got this right, notice that this one actually starts with ket minus 1, whereas this one also starts with ket minus 1. Now you might object by saying that there is no ket minus 1 in your space. The kets start with number eigenvalues of 0. And you would be right. But that makes no difference in this case because this square root of n factor here and the square root of n plus 1 factor corresponding to that one here ensures that this term corresponding to n equal to 0 here or n equal to minus 1 here actually is 0. So we can actually just change the limits here and start from 0 and count up to infinity. So that is what A acting on alpha is. On the other hand, because we are demanding that the ket alpha is an eigenstate of A corresponding to eigenvalue alpha, A acting on alpha must be also the same as alpha times alpha, that is simply alpha Cn times ket n summed over all n. Now these two expansions have to be one and the same. And because the ket n's are independent vectors, the only way these two expansions can be the same is if the coefficients match each other. So you must have the relationship Cn plus 1 root over n plus 1, this coefficient has to be the same as alpha times Cn. Or you could just rewrite this as Cn is alpha Cn minus the Cn plus 1 is alpha Cn by root over n plus 1, or Cn is alpha by root n Cn minus 1. And now I can repeat this because Cn minus 1 will be alpha by root n minus 1 Cn minus 2 and so on. So that you can keep on going right all the way down to C0 and get alpha by root n into alpha by root n minus 1 into alpha by root n minus 2 up to alpha by root 1 times C0. So this is a factor times the coefficient that you started out with. So Cn ultimately is given by alpha to the n by root n factorial times C0. So we have managed to express all the coefficients Cn of our ket alpha in terms of C0 times some multiplying factors. And therefore, ket alpha turns out to be C0 times this sum, from n equals 0 to infinity of alpha to the n by root n factorial times ket n. So we have managed to figure out what an eigenket of the operator A will look like up to at least a constant C0. We will return to this question of what this C0 should be later, but first let us see whether we can do the same thing with the operator A dagger. In other words, can we find an eigenstate of A dagger which obeys a rule like this? A dagger acting on ket beta should be beta times ket beta, where beta is some number. And once again, we assume that ket beta is a state which exists in our Hilbert space, so it can be expanded in terms of the number eigenstates with coefficients that we call dn. Now, applying A dagger on this and multiplying this by the number beta, equating the two gives us this relationship. And now we face a major problem. Notice that this side of the expansion starts with ket 0. Because you have applied the A dagger operator, the lowest state that you have here is ket 1. So there is no way these two could actually match. The vector on the left has no ket 0 on its expansion, whereas the vector on the right does. Now you might say that that's not too difficult to remedy. All you have to do is choose d0 to be 0 so that the ket 0 is not present here. However, this series has to start with some lowest value of n. d0, d1, d2, etc. can be 0, but it has to start at least some finite lowest value. Whatever that lowest value of n is on this side, if you apply A dagger on this, you are going to get a state whose expansion will have a lowest eigenvalue of n, which is 1 more. And therefore, there will always be a mismatch between the two sides. The lowest eigenvalue which is present in ket beta must of course be present in beta ket beta, but it will not be present in A dagger ket beta. In other words, it's impossible to maintain this equation. Thus, what we have seen is, although A does have an eigenstate, in fact has infinitely many eigenstates, one corresponding to each complex number alpha, A dagger, on the other hand, has none. Now it's also easy to see why A dagger has no eigenstate. It's simply because this Hilbert space that we have is spanned by a bunch of kets, eigenkets ket n, where the eigenvalue n has a lower bound, which means that every expansion has to start with a minimum value of n, and A dagger will give you a vector which has a minimum value which is 1 more, and therefore cannot match beta times ket beta. Now the same problem does not arise in the case of A, because although A lowers the eigenvalue, the spectrum of n hat is actually not bounded above. If it had been bounded above, then you would have had some maximum value of n in your starting state, and A acting on that would have lowered that value by 1, and then also it would have been impossible for A acting on ket alpha to have been equal to alpha times ket alpha. Can we say this from a more elementary viewpoint? From the position picture, for example. Now in the position picture, the operators A and A dagger can obviously be obtained from these abstract versions just by replacing x hat by the operator which multiplies by x and p hat by h cross by I d dx. If you did that to A hat, you will end up with this operator. Now, the eigenvalue equation A hat acting on a ket gives you alpha times a ket translates in the position picture to this operator acting on a wave function is alpha times the wave function. And this leads to a very straightforward and simple differential equation. It's a first order differential equation which can be easily rewritten to express d psi by psi in terms of this. Of course, there is a dx missing here, which I should have put in. And this is a very easy thing to integrate, and this ultimately leads to the result that psi is a times the exponential of minus m omega x square by twice h cross plus root over twice m omega by h cross alpha x. Now those of you who are familiar with the harmonic oscillator energy eigenstates would immediately recognize this as the ground state energy eigenfunction, and that shouldn't come as a surprise. Remember, the ground state is an eigenstate of a hat with eigenvalue alpha equal to 0. So if you drop this term, you do get the eigenstate corresponding to the ground state. But you notice that all this has done, this extra term, is that it has shifted the origin from 0 to a different value. So all that this does ultimately is that it gives you a shifted ground state wave function, or rather a shifted Gaussian wave function, which would have been the ground state wave function if it had not been shifted. So that is what a coherent state for a harmonic oscillator looks like in the position space. Now, since all we had to do here was to solve a standard simple differential equation, and since A and A dagger operators look very similar, it's just a matter of a change of sign, the ddx changes to minus ddx, and that's all that happens. The same should be applicable to A dagger as well. So, how can we explain the fact that we have just discovered that A dagger has no eigenstates? To understand this, all we have to do is carry out the same calculation, this time for A dagger. And if we do and solve this differential equation, you will get a very similar looking solution. Some other normalization constant A bar times this wave function, which also looks very similar. But there is one very big difference here. Because the ddx term changed sign, in this case, what has happened is that this exponent also has a change in sign. In particular, the quadratic term which dominates when you take x to large values now has a positive sign in front of it. In other words, this wave function blows up for large values of x and hence is definitely not normalizable. It does not belong to our Hilbert space, which remember is a space of normalizable wave functions. Now, this is something we have already stated before, but let me formally put this on record. The ket alpha that we have found out, the eigenstate of the operator A corresponding to eigenvalue alpha, is called a coherent state. Now, the name coherent state comes from the fact that this is related to the concept of coherence in optics, but that is a different story. We are not going to go into that right now. Now, as we have already stated before, to fix this constant C0, the overall constant, we must take a look at the normalization of the state ket alpha. So, if we take the overlap of the ket alpha with itself, it's obvious that what we need to do is take the bra for this ket and apply that on this ket itself, and that will give us C0 mod square times the sum over n and n prime. You have to remember that there are two sums here and you have to change one of the summation indices to a different value. So, you will end up with alpha bar to the n by square root of n factorial coming from the bra corresponding to this. That's why the alpha has changed to alpha bar. Here by bar I denote the complex conjugate. Times alpha to the n prime by square root of n prime. Of course, the bra here had a ket n and the ket has a ket n prime, and that's what this overlap is here. But we do know that this can be simplified drastically. This overlap is nothing but the Kronecker delta symbol, delta n prime, and if we just use the properties of the delta symbol, this sum simplifies drastically. Instead of a sum over both n and n prime, it becomes a sum over only n, where all the n primes are essentially replaced by n. That leaves us to alpha bar alpha to the power n in the numerator, and square root of n factorial twice becomes just n factorial. And this is a very well known sum, the sum for the exponential of alpha mod square. Equating this to 1, which is one possible way of demanding normalization, the most common way, will lead us to a modulus of C0 to be equal to a to the power minus alpha mod square by 2. So we have found out C0 up to an overall phase factor, and just by choosing that overall phase factor to be just 1, we usually write down the normalized coherent state ket alpha in the following form. It has e to the minus alpha mod square by 2 as an overall factor, and then you sum up over all n from 0 to infinity of this quantity alpha to the n by square root of n factorial times ket n. Now, for reasons that will be clear later on, when we are dealing with path integral quantization using coherent states, the coherent states that we use are not normalized ones. Rather, what we use is a choice of C0 equal to 1. So, if we make that choice, our coherent states take this particular form. Note that I have made a slight change in nomenclature or rather labeling here. I will typically use Greek letters like alpha, beta, etc. when we are dealing with normalized coherent states. But when we are dealing with coherent states with C0 equal to 1, the kind we are going to use in path integral quantization, we are going to use letters like Z, X, Y and so on, Latin letters from near the end of the alphabet. I am not claiming that this is some kind of standard that everybody uses, but it actually is a quite useful thing to keep in mind, especially because very often while dealing with path integrals, we will need to worry about the functional forms or behavior of these as functions of the complex variable z, and z after all is a standard notation that we often use for complex numbers. So that's the kind of labeling we are going to use for our coherent states, the ones we are going to use in path integral quantization. Near the end of this lecture, I am going to return back to normalized coherent states, where I am going to call it ket alpha again. Now, with this small matter of the labeling out of the way, let us take a look at the properties of this particular ket, the ket z. Well, one thing that you can immediately see is that you can write the ket n here in the form where the raising operator a dagger acts n times on the ket 0, of course with the extra factor of square root of n factorial. And because you now have two square roots of n factorials, you end up with one overall n factorial in the denominator, and the z and the a daggers combine to give you z a dagger raised to the n. So what we have is that the coherent state that we are talking about now can be obtained by applying this operator on the ket 0, and this operator is nothing but the exponential of z a dagger. Now the corresponding bra, the bra corresponding to this coherent state z, is going to be simply given by the bra 0 acted upon by the adjoint of this operator, which is e to the power z bar a. Let me remind you once again, z bar is the complex conjugate of the complex number z here. Now we already know that the operator a, when it acts on z, must give you z times the ket z. This is nothing but the eigenvalue statement that we have made about these coherent states. But what happens if a dagger were to go and act on this ket z? The result is pretty easy to work out. You just start with the expansion of the ket z, z to the n by square root of n factorial ket n summed over all n, apply a dagger on it. Of course, the a dagger goes and only attacks the ket n, giving you root over n plus 1 ket n plus 1. And now, you can supply another square root of n plus 1 in the numerator and the denominator and write this as root over n plus 1 factorial n plus 1 times ket n plus 1. Now, given that there are so many n plus 1s here, it is obvious that it will be easier to handle this if we were to replace n plus 1 by n or n by n minus 1, and this is what you are going to end up with. So notice what has happened. Your original ket z had z to the n by square root of n factorial ket n summed over all n from 0 to infinity. Here, what you have is a sum which goes from 1 to infinity or from 0 to infinity just as well, because the n equal to 0 term here will be 0 anyway. And what you are actually summing up is essentially the same thing, but with z to the n replaced by n z to the n minus 1. Now, how do we get n z to the n minus 1 from z to the n? Simple, just by differentiating with respect to z. So, basically, this expression is nothing but del z of the original thing that we started out with, that is del z of the ket z. We can also figure this out in an alternative fashion. Remember, we have already found out that ket z is nothing but this operator e to the z a dagger acting on ket 0. You are applying an extra a dagger on it. Now, if you were to differentiate e to the z a dagger with respect to z, what you are going to of course have is an extra a dagger. And that simply means that this whole thing, given the fact that ket 0 does not depend on z at all, is simply del z of e to the z a dagger ket 0 or del z of ket z as we figured out. Now, you may be a bit concerned about my rather cavalier use of del z on e to the z a dagger. Of course, if instead of a dagger you had some number, let's say small a or small alpha here, then del z of e to the z alpha would simply be alpha times e to the z alpha, which is essentially what we have used here. Does this also work when you have operators in this expression? In general, trying to use these results from ordinary mathematics into places where you are using operators may lead you into trouble, simply because operators would refuse to commute sometimes, and therefore some of these results which do depend on the commutativity of the objects involved will not work out. However, here there is only one operator involved, that's a dagger, and as a result, a partial derivative with respect to z will involve only commuting objects, and therefore we can use our standard high school mathematics formula perfectly well here. Now, if you put all of these together, what you get is the following. As far as the ket z, the coherent state, is concerned, the action of a on it is just multiplication by z, whereas the action of a dagger on it is just the action of the partial derivative del z. Now, because we are going to need this later on, I have also written down the corresponding results for the bras, which essentially can be found out simply by taking adjoints of these results that you have written down. Or you could start with the bra z written down in terms of z bar, sum over n goes from 0 to infinity bra n, z bar to the n by square root of n factorial. And just carry out the same calculations and you will immediately find the corresponding results on the right there. The upshot of all this is, as far as the kets are concerned, the operators z and del z provide representations of the algebra of the lowering and raising operators a and a dagger respectively. And this is going to be of great importance when we go over to path integral quantization using coherent states. Now, another property that is going to be very important for us is that of possible orthogonality of these coherent states. Now, the coherent states, as we have seen, are eigenstates of the operator A. Now, we do know that eigenstates of a Hermitian operator belonging to different eigenvalues are automatically orthogonal to each other. Since the operator A is not Hermitian, that result does not really work here. In fact, we can check by direct calculation that z and z prime to coherent states belonging to different eigenvalues z and z prime for the operator A are actually not orthogonal to each other. If we start with our non-normalized C0 equal to 1 version of coherent states, then it's easy to see that the overlap between z and z prime is going to be given by this. This is the bra corresponding to the ket z, and this of course is the ket z prime. And when you calculate this overlap, All you have to worry about is the fact that n and n prime, these are orthogonal to each other, being eigenstates of the Hermitian operator n hat, and therefore the overlap gives you delta nn prime. They are of course also normalized, and using the property of the conical delta symbol, this overall thing simply becomes z bar z to the power n by n factorial summed over all n, or e to the power z bar z. Now, while I did say that we are going to use these unnormalized coherent states for path integral quantization, it is actually easier to appreciate the significance of this result if we were to return, for the time being, to the normalized version. So, if you go back to the normalized version, the overlap between two coherent states alpha and alpha prime will be calculated almost exactly in the same manner. You will get e to the alpha bar alpha prime from the calculation, but in addition, what you will also get are two factors which come from the normalization. E to the minus alpha mod square by 2, which will come from this particular state, and e to the minus alpha prime mod square by 2, which will come from this state. And it's easy to see that the modulus overall thing is simply given by e to the power minus alpha prime's modulus square by 2. So what we have found out is even for normalized coherent states, the overlap does not vanish when alpha and alpha prime are different. Of course, it's equal to 1 when alpha and alpha prime are equal, but that's just a normalization that we are using here. But do note one very important thing. If alpha and alpha prime are far away from each other on the complex plane, then modulus of alpha minus alpha prime is nothing but the distance between those 2 points, and that becomes a large positive number. So e to the power minus modulus square of alpha minus alpha prime divided by 2 becomes very, very tiny. So although these coherent states are not really orthogonal to each other, they become approximately orthogonal as long as alpha and alpha prime are points which are distant from each other on the complex plane. Now, the coherent states play a role in path integral coherent state quantization, which is analogous to the role which position and momentum eigenstates play in the usual versions of path integral quantization, the ones we have studied before. You must remember that the overlap of a position eigenstate, for example, with the ket describing a system is nothing but the wave function describing the system. We expect to find something analogous to the wave function in the case where we are using coherent states. And to see what that is, let us first start with the statement that an arbitrary state ket psi can be expanded in terms of the basis vectors ket n in an expansion which looks like this. And here, what we have done is we have decided to write the coefficient in the form psi n by root n factorial. That is, we have added an extra factor of root n factorial, and the reason behind that is simply that it makes the later formulae easier to handle. Of course, the one obvious reason why you have a root n factorial is that if you use the fact that ket n is a dagger n by root n factorial acting on ket 0, this gives you a simpler looking final form. Psi n by n factorial a dagger to the n ket 0, and this is what makes taking the overlap with the coherent state Z easier, because when you calculate that, what you end up is with this particular matrix element. The matrix element bra Z a dagger to the n ket 0, and since the action of a dagger to the n on bra Z can be just found out by repeating the action of a dagger on the bra Z, that is one factor of Z bar every time, what you end up with is Z bar to the n times this particular overlap between the coherent state Z and the ground state 0. This is of course nothing but C0, or rather more precisely the conjugate of C0, which we have taken to be 1 in our case. So what we end up with is that the analogous quantity to the wave function, the overlap between Z and psi, is given by this particular function sitting here, the sum over all n from 0 to infinity of psi n Z bar to the n by n factorial, which we have decided to call psi of Z bar. This is of course just a notation, but you have to realize that something very important has gone into this notation. This is a function of z bar and z bar alone. In other words, it is an anti-holomorphic function of z. When we try to derive properties of the path integral, especially when we are going to talk about analyticity properties of the path integral, the consideration that this kind of quote-unquote wave function is actually an anti-holomorphic function of z is going to turn out to be very important. This is actually the reason why we did not bother putting in the normalization factor of e to the minus mod z square by 2 in the definition of our ket z here. We are going through the inconvenience of using a non-normalized coherent state because, on the other hand, it gives us the advantage of leading to a very simple analyticity property of the corresponding wave functions, overlaps of z and psi. If you had included the normalization factor, that would have led to an extra e to the minus mod z square by 2, and because mod z square has both z and z bar in it, it would neither be a holomorphic nor an anti-holomorphic function. As it stands, the overlap between psi and the corresponding ket z is of course the conjugate of this quantity, and that's written as psi bar of z. The argument here indicating clearly that this is a holomorphic function of z. These are going to be pretty important properties for our study of coherent state path integration. Now, if you know the wave function in position space, you can use that knowledge to reconstruct the abstract ket psi from it. All you have to do is use the fact that the position eigenstates form a complete set. So, a natural question to ask here would be, what is the issue with completeness as far as the coherent states are concerned? Now, just to remind you, what I said a while ago is just this. Any ket psi can be written down as an expansion in position eigenkets just by using this construct here, which is nothing but the identity operator written in terms of the completeness of position eigenkets. Now, something very similar, of course, also exists for other complete sets of eigenstates. For example, the number eigenstates are complete, they are discrete. So here, instead of an integration, you have a simple summation for all values of n of the ket n bra n combination, and that is going to be equal to the identity. The question that we have is, do we have something similar with ket z bra z combinations? If you were to somehow sum them up over all values of z, and z being complex numbers, you would somehow have to sum up over both real parts and imaginary parts, would you get the identity? To see whether that is true, what we need to do is take a look at this quantity, the ket z bra z combination, which is the sum over n and n prime running from 0 to infinity of the quantities z to the n z bar to the power n prime, square root of n factorial square root of n prime factorial times the ket n bra n prime. Now what we need to do next, as I said, is integrate this over the complex plane, and one way to write an integral over the complex plane could be to use d of the real part of z times d of the imaginary part of z as your measure, or you could also equally well use dz bar dz as the measure. As it turns out, it is actually easier to calculate the integral in so-called complex polar coordinates, or rather use the magnitude of z, rho, and the argument phi as the variables. So what we need to do is be able to change our variables z bar and z to the variables rho and phi and determine what the connection between the respective measures will be. For that, of course, all you need to do is calculate the Jacobian of this transformation, this del z bar z del rho phi, which is just the determinant of this matrix formed by taking the derivatives of z bar and z respectively with respect to rho and phi. The calculation works out pretty simply, and you can easily figure out that ultimately this particular Jacobian is actually twice I rho. And therefore dz bar dz is twice I rho d rho d phi. So this is what we are going to use, because when we want to evaluate this quantity, z to the n, z bar to the n prime, these are of course factors which we had from the ket z bra z combination. What we need to do is throw in an extra factor of e to the minus z z bar, and that, when you integrate over z bar and z, translates to this integral over rho and phi. The dz bar dz changes into twice I rho d phi. The e to the minus z z bar of course becomes e to the minus rho square, and z to the n, z bar to the n prime gives you rho to the n plus n prime times e to the I phi n from z to the n, and e to the minus I phi n prime from z bar to the power n prime. Now this of course is an integral in which phi goes from 0 to 2 pi and rho goes from 0 to infinity. Now the phi integral is really very easy to do and should be very familiar to all of you, and a direct calculation will convince you that this is equal to 2 pi when n equals n prime and equal to 0 when n is different from n prime. So this is really 2 pi delta n prime. So after evaluation of the phi integral, this is what happens. Twice I is a factor which has come out of the integral. 2 pi delta n prime is nothing but the value of the phi integral, and you are left with rho d rho times e to the minus rho square, rho to the n plus n prime. And because the delta function forces n prime to be equal to n, you can actually replace n prime by n in the integral as well, and then just use the substitution rho squared equals t to reduce this to this very familiar integral, which happens to be equal to n factorial. Note that it is the presence of this e to the minus z z bar factor which actually allows you to get a familiar value for this integral. Well, not only that, it actually allowed you to carry out the integration at all, because without this factor, the function in the integral would have grown too large at large values of mod z, and this integral would not have converged. This e to the minus z z bar factor essentially makes the integral converge to a finite value. Now that we know this integral, what we are going to do is simply take e to the minus z z bar times our ket z bra z combination, integrate over the entire complex plane, and because we already know what e to the minus z z bar z to the n, z bar to the n prime integral is, namely this one, we can just use our expansion of ket z bra z in terms of the n's, which we worked out a while ago, and then simply carry out this integral over z bar and z, use the fact that this is a very simple integral, ultimately 2 pi I delta n prime n factorial, and this delta n prime helps you to calculate the n prime sum trivially. All that happens is all the n primes get replaced by n, and now what you see is that this n factorial gets cancelled by this quantity in the denominator after you put n prime equal to n, and you are left with 2 pi I times the sum over all n of the ket n bra n, and this of course is nothing but the identity. So our integral of e to the minus z z bar ket z bra z over the entire complex plane works out to be 2 pi I times the identity. Once again, you should realize that e to the minus z z bar is a factor that we had to put in simply because we had not used normalized eigenkets. Also, because the eigenkets actually are not orthogonal to each other. But once we do that, we end up with this version of the completeness relation between coherent states, which is this particular integral is equal to the identity, and that means that in terms of our functions psi of z, we can actually expand any ket psi. The ket psi will be simply the identity, this quantity, applied on the ket psi. And because this thing we have already called psi of z bar, what we end up with is the ket psi can be written down in terms of psi of z bar times e to the minus z bar z. This is an extra factor that the normalization demands, multiplied by ket z and summed up over all possible values of the complex parameter z. Now it so happens that the coherent states are actually over-complete, in the sense that even if you remove a large number of them from the set, the remaining coherent states still form a complete set. Now that's a technical point which we will not need to worry too much about in the rest of our lecture, so I'm not going to bother too much about that point. What I will now do is describe a very important result which is going to be extremely useful when we come to the calculation of path integrals using coherent states, and that is the statement that you can actually write the matrix elements of any operator in terms of coherent states. And not only that, it follows that if you have ensured that your operator is in the normal order, then the calculation of the matrix element becomes very, very simple. Let me remind you that an operator constructed by using raising and lowering operators a dagger and a is said to be in the normal order if it is a sum of terms such that the lowering operator a is on the right of the raising operator a dagger. This ensures that the matrix element of such an operator in the ground state of the harmonic oscillator will vanish. This becomes even more important when we are talking of the field theoretical case, where normal ordering of physical operators like, say, the Hamiltonian becomes essential to avoid infinite zero-point energies which would otherwise plague such theories. So let us now examine what the matrix element of a normal ordered operator will look like if we write that in terms of the coherent states. To see this, let's start with the simplest possible kind of normal ordered operator, a product a dagger raised to the power m times a raised to the power n. If you sandwich this between two coherent states z and z prime, a dagger to the m acting on z will bring out a factor of z bar to the m, and a to the n acting on z prime will simply give you z prime to the n. And then of course you are going to be left with z bar prime, the overlap. So the result is z bar to the m, z prime to the n times e to the power z bar z prime, which is of course nothing but the overlap between z and z prime. For any normal ordered operator, a general normal ordered operator, the form would be a dagger m a to the n, terms like these multiplied by coefficients a, m, n, and summed up over all possible values of m and n. And for any such operator, the matrix element between z and z prime is simply going to be this function amn z bar m z prime to the n times e to the z bar z prime summed over all m and n. And basically, what we see is apart from this e to the z bar z prime factor, the rule for figuring out the matrix element between any operator A, which is a function of a dagger, and A, the raising and lowering operators, is simple. All you have to do is everywhere where you have a dagger in your operator, you replace that by z bar, and everywhere where you have a in the operator, you replace that by z prime. So this becomes a simple translation rule which works. A gets replaced by z prime and a dagger gets replaced by z bar. And if you do that, then you can immediately write down the matrix element between coherent states of any normal ordered operator whatsoever. It is a simple dictionary which relates operators which are normal ordered on the one hand with their matrix elements on the other that makes calculations using coherent states rather simple. We now have enough properties of coherent states under our belt to start investigating path integral quantization using them. That is going to be the topic of our next lecture. However, there are many other interesting properties of coherent states which go beyond just path integral quantization, and I can't resist at least mentioning a few. One of them is the fact that if you start instead of this C0 equal to 1 coherent state, but start with the normalized coherent state, what you have, of course, is an extra factor of e to the minus alpha mod square by 2. Remember once again that when we are talking of normalized coherent states, I am going to use the label alpha for the eigenvalue. So this can be written down in another clever way by introducing this additional operator e to the minus alpha bar a hat. If you think about it a bit, since a hat actually annihilates ket 0, e to the minus alpha bar a hat, which is actually identity minus alpha bar a hat plus 1 by 2 factorial minus alpha bar a hat whole square and so on, acts on the ket 0 to just give you the result of identity acting on ket 0, namely ket 0 itself. So introducing this extra factor has not changed this in any way. What it has done is that if you make use of a rather familiar formula involving operators, the so-called BCH formula, you will end up with e to the alpha a dagger minus alpha bar a hat as the combination up here. Remember, a dagger and a hat do not commute, and because they do not commute, you cannot use the formula e to the a plus b is e to the a times e to the b, which is familiar to us from elementary mathematics. The non-commutation actually leads to an extra factor, and that extra factor is what the BCH formula gives you. This particular operator is called d alpha, which acts on the ket 0 to give a normalized eigenket alpha. And the beauty of this operator, of course, is that it is an unitary operator. Note that alpha a dagger minus alpha bar a hat in the exponent here is actually an anti-Hermitian operator, and when you exponentiate an anti-Hermitian operator, what you get is a unitary operator. And therefore, it's not a surprise that the resulting ket alpha is actually normalized. So this unitary operator is called the generator of coherent states, and many of the important interesting properties of coherent states can be figured out by just using this operator. I will just mention quickly some results. I will just skip over the details here, but one result that you can find very interesting is the following. D dagger alpha a d alpha, this unitary transformation of a hat, which this unitary operator d alpha carries out, is a simple translation. A hat gets changed by 2 a hat plus alpha times the identity. And the similar thing happens to a dagger. A dagger gets changed to a dagger plus alpha bar times the identity. If you take this expression and apply it on ket 0, what you are going to get is a hat plus alpha identity acting on ket 0, and since a hat kills ket 0 off, you are going to simply get alpha times ket 0. And remembering that d dagger alpha is actually the inverse of d alpha, you simply end up with this expression, which is nothing but the statement that a operator acting on the state ket alpha is alpha times ket alpha. There are many other interesting applications of this displacement operator d alpha. We will not be able to go through all of them in this lecture, and in any case, that's really not our aim here. I will just end by mentioning one very important property, which you can prove by using either this d alpha ket 0 version for ket alpha, or by using the standard normalized expansion for the coherent states. This involves the issue of the expectation value of x and p, x square and p square, or more importantly, the question of the variance delta x times the variance delta p. the so-called uncertainty product. Now, X and P are related to A and A dagger by this simple relationship. These are of course inverses of the relationships that we had written for A and A dagger in terms of X and P earlier. And using these, it's very easy to see, for example, that if we were to calculate the expectation value of X in a coherent state, it's the same as d alpha ket 0. This is of course ket alpha. And bra 0 d dagger alpha. This of course is bra alpha. Sandwiching X hat. And by substituting the expression for X hat, what we end up is the matrix element or the vacuum expectation value of this quantity is what we are looking for. And simply by using the results that carrying out d dagger alpha operator T alpha, this kind of similarity transformation on A and A dagger has the results that we had just mentioned above, we simply get the expectation value of X as this. And by noting that A and A dagger, both of them have exactly 0 expectation value in the ground state, leads us to this final result for the expectation value of X. By using a very similar technique, we can calculate the expectation value of X square. But what is of more interest to us is that once you calculate the expectation value of X square and using the expectation value of X that has been just calculated, you can evaluate the variance, or rather the square of the variance delta X, by calculating the expectation value of X squared and subtracting from it the square of the expectation value of X. And this calculation yields the result h cross by twice n omega. An almost identical calculation using the momentum operator reveals the result that delta p whole square is h cross m omega by 2. And this leads to the very interesting result that if you were to multiply delta x by delta p, you would get h cross over 2. And this is one of the reasons why the coherent state is of such great importance in quantum mechanics. It happens to be a minimum uncertainty state, a state for which the Heisenberg uncertainty principle is actually obeyed as an equality. Now, as I have said, there are many other interesting properties of coherent states, and indeed, there are other kinds of coherent states that we may have to talk about, like spin coherent states, fermionic coherent states, and so on. We will meet a few of them later on in this course, but for the time being, this is all I will have to say on the topic of coherent states. In the next lecture, we are going to make use of the results that we have learned in this lecture to evaluate path integrals using the coherent state formalism. Bye till then.